Today, we are going to be talking about the Laplace transform. So you should have received a handout from me. On the back of it, it has Laplace transform properties that have all been filled out, but we're going to go over them. And on the front, it says useful Laplace transform pairs, and the whole thing is blank on one side because we are going to sort some of that stuff out. Now, I know that you guys are super thrilled about the ridiculous amount of calculus that I've been forcing you to do and forcing you to watch me do over the past couple of days. And it would probably appall every single one of your math professors, but I'm going to show you how to do the Laplace transform of effectively all of those things, and I'm going to perform exactly one integral the entire time. So let's talk about what's going on here, okay? So Laplace transform. All right, so way back in circuits 1, and then again in circuits 2, because I couldn't trust you guys to have actually learned it in circuits 1, we analyzed circuits in the time domain and showed that for complex circuits where we had steady state sinusoidal excitation, analysis in the time domain was extremely difficult. And analysis in the frequency domain was much, much easier. So to summarize that process, we had something akin to this, right? So we had some time domain circuit. In our time domain circuits, and you guys probably remember this more freshly from circuits 2, we wound up with differential equations and then solved those differential equations in order to determine our time domain solution, which may or may not have involved a ridiculous amount of trig identities depending on what we were trying to solve for explicitly. As an alternative path, right? I'm just going to put a dashed line here representing the transition from the frequency domain, excuse me, the time domain into the frequency domain. So we could have instead, and this is what we learned late in circuits 1 and again in circuits 2, converted our circuit from the time domain into the frequency domain. Bless you. Used algebraic equations to figure out what was going on. Came up with some frequency domain solution. And then converted that frequency domain solution back into the time domain. So this was all hunky-dory when we were dealing with steady state sinusoidal circuit analysis. But what if our circuit of interest is excited by something that isn't a steady state sinusoidal excitation signal? So an everlasting sinusoid that exists from t is equal to negative infinity out to t is equal to positive infinity. And that is where the Laplace transform comes in. So the Laplace transform is effectively going to allow us to perform our traditional frequency domain analysis and all of that kind of stuff on pretty much any system that we could think of to realize. Okay. So let's define the Laplace transform. So if I have a function that is not how you spell function. The Laplace transform of f of t is defined to be, so I'm going to use a big curly Laverne and Shirley L. So the Laplace transform of our function f of t will be the integral from 0 minus to infinity. So that is the instant before t is equal to 0. So I am taking into account any stored energy in capacitors and inductors by starting my integral at 0 minus of f of t times an exponential e to the negative st dt. And this will give me some function of s. So the capital F is the Laplace transform, capital F in what I'm going to call the S domain is the Laplace transform of a function lowercase f in the time domain. Okay. And this technically is the unilateral Laplace transform. There is a bilateral Laplace transform in math, but because we deal only with causal systems and causal signals, I don't care about what's happening from negative infinity up to 0 minus, so I'm just throwing all of that away because it should always be 0 for any system that we could possibly realize. So that operator S is the complex frequency which is defined as S is equal to lowercase sigma. Sorry, I can't draw that Greek letter better than that, but that's what it's supposed to be. Lowercase sigma plus j omega. So effectively, what we can actually glean from this thing, and it won't be obvious just yet, but all of our steady state sinusoidal circuit analysis that we have done in our previous classes is actually a special case of the Laplace transform, where sigma, the real component of our complex frequency S, is just assumed to be 0. So effectively, this coefficient here, or this portion of our complex frequency S, is what's telling us how our signals exponentially increase or exponentially decay. And the j omega part tells us how our signals oscillate as a function of time. So this is literally just steady state sinusoidal portion of our S operator here. So the function lowercase f of t and capital F of s are called a Laplace transform pair, and a given function f of t has a unique Laplace transform f of s, and vice versa. Depending on the functional form of f of t, the Laplace transform integral may or may not converge to some finite value. If the integral does not converge, then we do not have a Laplace transform for that particular function. Okay. So to put it another way, for f of t to have a Laplace transform f of s, then the integral from 0 minus to infinity of the magnitude of f of t e to the negative st dt would be the same as the integral from 0 minus to infinity of the magnitude of f of t times the magnitude of e to the negative sigma t times the magnitude of e to the negative j omega t dt. And all of this looks like the integral from 0 minus to infinity of the magnitude of f of t e to the negative sigma t dt must be less than infinity for a real, that looks even less like a sigma, sorry about that, for real sigma. So just to be super clear, the reason why I was able to get rid of this thing is the magnitude of e to the negative j omega t is literally always 1. Because that is just, this thing effectively defines a unit circle in the complex plane. So its magnitude is always exactly 1. So if, let's see, I'm sorry, what? They are from 0 minus to an infinity. So all of these are from 0 minus to infinity. Okay. So we have a pretty well-defined Laplace transform. So now let's talk about the inverse Laplace transform here really quickly. Okay. So the inverse Laplace transform of a function f capital S is defined as, so big Laverne and Shirley L with a -1 superscript to let us know that we're doing the inverse, is 1 over 2 pi j times the integral from sigma minus infinity to sigma plus infinity of f of s e to the st dt, which just returns our function. Technically speaking, there's also a constraint on this. We need sigma to be less than sigma sub c, where sigma sub c is the smallest value of sigma for which the integral converges, but we're not going to really worry about anything like that. So what we have here for our inverse Laplace transform is integration over the complex plane. How many of you guys know how to do that? For what it's worth, I haven't done it since I was in graduate school, where I learned specifically to do it because I took a class on it on account of me being a big giant nerd. Never done it since. So as opposed to figuring out the mechanics of performing this integration over the complex plane, we will instead just use the relationship between Laplace transform pairs. So if we have a function with a well-defined Laplace transform, well, if we recognize that Laplace transform, we can just say its inverse Laplace transform must be the f of t. that gave us that originally. So we will never, ever do that ugly complex integral. Okay. So now let's talk about properties of the Laplace transform. And our first one is going to be the linearity property. So this is extremely similar to what we covered when I talked about linearity way back in circuits 1 for those of you that had me. Okay. So if we have some function f of t that can be decomposed into some arbitrary constant k1, value does not matter, it does not have to be real, just needs to be constant, times some function f1 of t plus some arbitrary constant k2 times some second function f2 of t, then the Laplace transform f of s will be equal to k1 times f1 of s plus k2 times f2 of s. Effectively, read this as I can scale my time domain functions by any arbitrary constant, and that results in scaling my Laplace transform by any arbitrary constant. I can add together two functions in the time domain, and it will give me a Laplace transform that is just the sum of the two functions in the S domain. So we have both the homogeneity and the additivity property of linearity represented here in the Laplace transform. Okay. If we wanted to prove that, the Laplace transform of k1 times f1 of t plus k2 times f2 of t is going to be simply the integral from 0 minus to infinity of k1 f1 of t plus k2 f2 of t. Excuse me, I need to multiply by my e to the st, or e to the negative st dt. Because my integral operation is a linear function, I can just effectively split this up into two distinct integrals. So I'll have an integral from 0 minus to infinity of k1 f1 of t e to the negative st dt, plus an integral from 0 minus to infinity of k2 f2 of t e to the negative st dt. I can take my constants k1 and k2 to the outside of my integral, so that's going to be k1 integral from 0 minus to infinity of f1 e to the negative st dt plus k2 integral from 0 minus to infinity of f2 e to the negative st dt, and that integral from 0 minus to infinity of all of this is just the Laplace transform a function f1 of t. This integral over here is just the Laplace transform of our function f2 of t. So this gives me k1 f1 of s plus k2 f2 of s. Our second property is the time scaling property. which effectively says that if I stretch my time axis by some factor of a, this corresponds to a shrinking of the s-axis and amplitude of my Laplace transform by the same factor and vice versa. So I will get a Laplace transform of 1 over a times f of s divided by a for some positive value of a. And once again, we'll do a quick proof of why this works. So if I have a Laplace transform of f of at, this is by definition the integral from 0 minus to infinity of f of at e to the negative st dt. I am going to define a new variable, tau, that is equal to at, and thus dt will be 1 over a times d tau. Are we okay with that? So effectively, if I divide through by a on both sides, and I take the derivative of t, I'll get 1 over a. Okay, so from here, I can just substitute in for at. And so that's going to give me the integral from 0 minus to infinity of 1 over a f of tau e to the negative s over a times tau d tau. And now I'm simply going to define another extra variable. X is equal to s over a. I can pull out my factor of 1 over a. So that gives me the integral from 0 minus to infinity of f of tau e to the negative x tau d tau, where this integral is just a Laplace transform as a function of tau, right? So that I would have, or x is effectively just taking the role of s, and tau is taking the role of t in my definition for Laplace transform. So this gives me 1 over a f of x, which is the same thing as 1 over a f of s over a. So once again, if I stretch my time axis by a, I shrink my Laplace transform by a factor of a, and I also scale its amplitude down by a factor of a as well. So that's time scaling. Now we will look at time shifting. So for a function f of t minus capital T, sorry, I don't want to throw another tau in there just yet, u of t minus capital T, so just a function multiplied by a unit step function, both shifted by the same amount, I will have a Laplace transform of f of s multiplied by e to the negative capital T times s, as long as t is greater than or equal to 0. And again, the reason why we're putting, oh, I forgot the capital T here. The reason why we're putting the constraint on this thing for capital T to be greater than or equal to 0 is to make sure that we are just shifting stuff to the right so that we always have causal signals and responses and all of that kind of stuff. If we allow this capital T to be negative, that means that our stuff would be time shifted to the left, starting before T is equal to 0, which is outside of the bounds of our integral. So we can't let that happen. So the Laplace transform of our generic function that is time shifted will be equal to the integral from 0 minus to infinity of f of t minus capital T u of t minus capital T e to the negative s lowercase t dt. So what's the value of this unit step function over this interval? 1, right? Because we're saying this doesn't turn on until some point in time that's later, but when it's on, it's always just going to have a value of 1. So we're just going to let that look like 1. So just to be clear, this thing goes to 1. So this will give us the integral from capital T to infinity, because everywhere from 0 minus to capital T has to be 0, because this guy was 0 over that interval. F of t minus capital T e to the negative s lowercase d dt. Let's let x be equal to t minus capital T. And from this, dt is just dx. So this gives us the integral from capital T to infinity of f of x e to the negative s of x plus capital T dx. And I can break that exponential function up into an e to the negative sx times an e to the negative s times capital T. That e to the negative s times capital T is a constant with respect to variable x, which means I can pull it outside. And so this gives me e to the negative s times capital T of t to infinity f of x e to the negative sx dx, sorry, or f of s e to the negative t times s. Effectively, that's already taken to account here. So this is effectively kind of like creating a new 0 point in our system, because we're saying x is just our time shifted time. So we've got everything encapsulated by changing our bounds from capital T to infinity, because we know that this function multiplied by that unit step function is 0. The product of those two things has to be 0 up until the point capital T. All right, let's look at our frequency shifting property. So if I have some function f of t and I multiply it by an exponential e to the negative at, that will give me a Laplace transform of f of s plus, sorry, that should be a. Okay. So you may be thinking to yourself, how is this frequency shifting? Well, really, we would read it the other way around, right? So we know that S is our complex frequency. If I shift that complex frequency by some amount A, it results in my original function multiplied by this extra exponential thing. Because the whole point is that the Laplace transform exists in the frequency domain, and all of the stuff on the left-hand side is our time domain stuff. So this one's pretty straightforward to prove. So if we take the Laplace transform of e to the negative at times f of t, we'll have the integral from 0 minus to infinity of f of t e to the negative at e to the negative st dt. I can just lump those two exponentials together. So that would give me the integral from 0 minus to infinity of f of t e to the negative s plus a t dt, which has a Laplace transform of just f to the s plus a. So literally all we're doing is replacing our original s with s plus a. Time differentiation. So this one can get a little wonky. So the derivative with respect to time of some function f of t has a Laplace transform of s times f of s. So just my Laplace transform of my original function multiplied by a factor of s. And then I need to subtract from that lowercase f at 0 minus. So effectively, I need to take my initial condition into account on the system. Okay. So for proof of this, the Laplace transform of the derivative of f of t with respect to time would look like the integral from 0 minus to infinity of the derivative of f of t with respect to time multiplied by e to the negative st dt. Let's let u equal e to the negative st and v prime equal the derivative of ft with respect to time, so that v is just f of t and u prime is negative s e to the negative st. So just doing integration by parts here. So performing integration by parts, I'm going to have uv, so that is f of t e to the negative st evaluated at 0 minus and infinity minus the integral from 0 minus to infinity of negative s f of t e to the negative st dt. So, sorry, I have a question. So at infinity, e to the negative st looks like 0, right? So we're going to have 0 minus, and then whatever happens at 0 minus. Well, at 0 minus, e to the negative st looks like 1. So we're literally just going to have minus f at 0 minus. From that part right there. So minus f at 0 minus. This integration is occurring with respect to t, so I can pull this s out as a constant. My negative looks like a positive. So I will have plus s times the integral from 0 minus to infinity of f of t e to the negative st dt. Well, that's literally just the Laplace transform of my function, right? So putting these two things together looks like s, f of s minus f at 0 minus. So that's my first derivative. Higher order derivatives are effectively just repeating that process over and over and over again. So if I have a second derivative, this will have a Laplace transform of s squared times f of s minus s times f of 0 minus the derivative of f of t with respect to time evaluated at t is equal to 0 minus. Third derivative is just going to be s cubed f of s minus s squared f of 0 minus s times the derivative of f of t with respect to time evaluated at t is equal to 0 minus the second derivative of f of t with respect to time evaluated at t is equal to 0 minus, and so on and so forth until I get to the nth derivative. Which is just going to look like s to the nth power times f of s minus s to the n minus 1 power times f of 0 minus s to the n minus 2 times the first derivative. Sorry, this should be df of t. dt evaluated at t is equal to 0 minus. And then keep on iterating on that thing over and over again until we get to effectively s to the 0, which is literally just 1, the n minus 1th derivative, f of t over dt to the n minus 1 of t at evaluated at t is equal to 0 minus. Realistically, I don't expect us to ever have to do anything over the second derivative. So derivatives can be a little gross. Integrals are pretty dope. So property number 6, time integration. If I take the integral from 0 minus to some point in time t, excuse me, of f of tau d tau, this will have a Laplace transform that is just 1 over s times f of s. So effectively, integration in the time domain looks like multiplying by a factor of 1 over s in the frequency domain. So to prove this, we would have the Laplace transform of the integral from 0 minus the t of f of tau d tau will be the integral from 0 minus to infinity of the integral from 0 minus to t of f of tau d tau e to the negative st dt. So once again, doing integration by parts, we're going to let u equal to the integral from 0 to t of f of tau d tau, which would make v prime e to the negative st, which in turn makes v negative 1 over s e to the negative st, and u prime would be the derivative of the integral, which is just the function itself. So applying integration by parts, I'm going to scooch my equal sign over here a smidge. So I would have u times v, so that's going to look like negative 1 over s e to the negative st. Here's my multiplying by u, so 0 minus to t of f of tau d tau. Close that, evaluate this at 0 minus and infinity, minus the integral from 0 minus to infinity of v du. So that's going to be negative 1 over s f of t e to the negative st dt, like so. Looking at this guy right here on the left-hand side, so when we put in infinity, this first term is going to go to 0. When we put in 0 minus, we're integrating from 0 minus to 0 minus. So what's that integral going to give us? 0, because we're integrating over no time, right? So the whole first term winds up going away. The minus signs cancel each other out. So this minus times this minus becomes a plus, and we literally just have the definition of the Laplace transform multiplied by a factor of 1 over s. So this looks like 1 over s integral from 0 minus to infinity f of t e to the negative st dt, or 1 over s f of s. Yes. This is literally on the back of the sheet that I gave you. Yep. Doesn't have the proof, but the actual thing is on the back of the sheet I gave you. All right, and then the last property that we're going to talk about, and there are more that you guys might see in your linear systems and signals class, but they're not that any that I give a shit about because I'm teaching you circuit analysis. So the last one that we're going to deal with, number 7 here, is the time convolution property. And this is the real reason we're using the Laplace transform in this class. Okay. So property 7, time convolution. So the time convolution property states that if I have a function f1 of t convolved with a function f2 of t, then the Laplace transform of this convolution operation is just the Laplace transform of f1 of t multiplied by the Laplace transform of f2 of t. So convolution in the time domain effectively looks like multiplication in the frequency domain, which means those terrible integrals and stuff that I made you do in your last homework set literally just look like multiplication if we can figure out what the Laplace transform of those signals or things is. Okay. So just for the sake of consistency to prove this, the Laplace transform of f1 of t convolved with f2 of t is going to look like the integral from 0 minus to infinity of the integral from 0 minus to infinity of f1 of tau multiplied by f2 of t minus tau d tau, close braces, e to the negative st dt. So we will let u equal to t minus tau, and we will let du equal, or actually we won't. If we let u is equal to t minus tau, then du is just d tau. So let's make some substitutions in here. Okay. So integral from 0 to negative, excuse me, 0 minus to positive infinity, not just changing the bounds on you guys to mess with you, times the integral from 0 minus to infinity of f1 of tau times f2 of u du e to the negative s. So just to be clear here, all I'm going to do is I'm going to move this tau over from the right-hand side of the equal sign to the left-hand side of the equal sign, so that where I had this t, I'm going to replace it with u plus tau. That guy right there, my mistake, should have been a d tau. Getting my double integration mixed up, I apologize for that. And I can split this exponential up into an e to the negative su times e to the negative s tau. No, this du should be du because I'm just replacing this dt here with the du. This d tau should have remained d tau. So that's going to look like 0 minus to infinity, 0 minus to infinity of f1 of tau times f2 of u d tau e to the negative su times e to the negative s tau du. So since this e to the negative su is effectively a constant with respect to tau, I can move it inside, right? And since this f2 of u is effectively a constant with respect to tau, I can move it over here. And so what that's going to wind up doing is effectively allowing me to split those integrals up, because I have everything with constants with respect to u in one integral and everything with constants with respect to tau in the other integral, so that I get e to the, excuse me, 0 minus to infinity of f1 of tau e to the negative s tau d tau multiplied by 0 minus to infinity f2 of u e to the negative su du, which is just f1 of s times f2 of s. Okay, so we have all of these properties. And now, like I said, we are going to start working on filling out our table of Laplace transforms. And I am going to use properties of the Laplace transform almost exclusively to fill out this table, okay? So let's start with the function f of t is equal to u of t. And this will be the only one that I'm actually going to do an integral for. Okay. So the Laplace transform of f of t in this case is going to be the integral from 0 minus to infinity. So I'm integrating with respect to time. What is the value of my unit step function over this interval? 1. So 1 e to the negative st dt. So this is a pretty straightforward and simple integral, right? So I'll pull out a factor of negative 1 over s e to the negative st, evaluate it at infinity and 0 minus. So that's going to look like negative 1 over s. E to the negative st at infinity gives me a 0. E to the negative st at 0 minus gives me a 1. And so this just looks like 1 over s. So the Laplace transform of the unit step function is just 1 over s. All right. Got a question? Negative, negative 1 over s. This one out here? The integral of e to the at is 1 over a e to the at. A is negative s. Okay. All right. So our next function that we're interested in is a Dirac delta function. Now, what do we know about the Dirac delta function? It is the derivative of the unit step function, right? So this is just the derivative of u of t with respect to time. So if we go and look at our time differentiation property, this should just be s multiplied by the Laplace transform of the unit step function, which is just 1 over s, minus f at 0 minus. What is the value of a unit step function the moment before it turns on? 0. So s times 1 over s is just 1. So the Laplace transform of a unit step function, or excuse me, the unit impulse function is literally just the number 1. let's say that we have f of t is equal to e to the negative at. I don't know why I keep using alpha, just used to it, I guess, from other things. E to the negative at u of t, right? So let's look at the frequency shift, or the frequency shifting property of the Laplace transform, right? So I could say that this guy right here is just some generic function g of t. So it should have a Laplace transform capital G of s of 1 over s, according to what we did up here, right? The Laplace transform of a unit step function is 1 over s. What does the frequency shifting property of the Laplace transform tell me that I can do? I would just replace s with s plus a, because my time domain signal is multiplied by a factor of e to the negative a of t. So from that, f of s is just 1 over s plus a. Just using frequency shifting property of the Laplace transforms. Now we're going to have a little bit of fun with trig. I mean a very small amount of trig here. Okay. So let's say that f of t is equal to cosine of omega t, u of t. Do you guys remember Euler's identity from circuits 1? Looks like you guys are drawing blanks. Okay. So just to refresh your memory, e to the jx, we did it as e to the j omega t, but I'm just going to use x right now so I don't have extra variables and all of that kind of stuff going on, is equal to cosine of x plus j sine of x. Is that familiar? You guys have seen that before, at least if you took me. Okay. So I can take this a little bit further, and I can say that e to the negative jx would be cosine of negative x plus j sine of negative x, right? Well, cosine of negative x is the same thing as cosine of positive x. And sine of negative x is the same thing as negative sine of x. So that will give me minus j sine of x. So if I were to add e to the jx plus e to the negative jx, what would I get? So e to the jx plus e to the negative jx is 2 cosine of x. So I'm going to express this cosine omega t right here as 1/2 e to the j omega t plus e to the negative j omega t multiplied by u of t, or 1/2 e to the j omega t u of t plus 1/2 e to the negative j omega t u of t. The reason why I'm doing this is because I already know what the Laplace transform of an exponential function multiplied by a unit step function is, right? We did it, oh, right here. So the Laplace transform of f of t is going to be 1/2 the Laplace transform of e to the j omega t u of t plus 1/2 the Laplace transform of e to the negative j omega t u of t. Sorry, that's running into each other. Okay. So what's the Laplace transform of e to the j omega t u of t? One over s plus a in this case is just j omega, right? Oh, okay. So to be clear here, so I heard somebody say, hey, I thought it was negative. So you are correct, right? So if we have e to the negative at has a Laplace transform of 1 over s plus a, then e to the positive at would have a Laplace transform of 1 over s minus a. Absolutely correct. So that should look like 1 over s minus j omega. Thank you for that. You're absolutely correct. So 1 over s minus j omega plus 1/2. So what should the Laplace transform of e to the negative j omega t? This is where we'll have 1 over s plus j omega. So actually, let me do something real quick here. I'm just going to, shit, that's not what I wanted to do. I'm just going to scooch this over so I can add something in there. Okay. So if I multiply by the complex conjugate of this denominator over the complex conjugate of this denominator, I'm going to get rid of the complex number in the denominator. Same thing here, right? So I'm just going to multiply by a fancy representation of the number 1. So that would be s plus j omega over s plus j omega goes here. S minus j omega over s minus j omega goes here. So that's going to give me 1/2 times s plus j omega over s squared plus omega squared plus 1/2 times s minus j omega over s squared plus omega squared. So let's see. So I have an s plus an s, so that's 2s divided by 2. The plus j omega and the minus j omegas are going to cancel each other out. So I should have just s over s squared plus omega squared. The last one that we'll do for today is going to be for a sine function. So just really quickly here, looking at these identities, if I do e to the jx minus e to the minus jx, the cosines will cancel each other out, and I will have j sine x minus negative j sine x. So e to the jx minus e to the negative jx looks like 2j sine x. Yes. So look at things here, right? I have s plus s. 2s in my numerator divided by 2 gives me just s. And then I have the s squared plus omega squared in the denominator. All right. So f of t is equal to sine omega t u of t. is the same thing as 1 over 2j e to the j omega t minus e to the negative j omega t u of t. So the Laplace transform of f of t should be 1 over 2j times the Laplace transform of e to the j omega t u of t minus 1/2, 1 over 2j, the Laplace transform of e to the minus j omega t u of t. And now we're just going to use the exact same things we did in the last example. So we're going to have a factor of 1 over 2j. This is going to look like 1 over s minus j omega. I'm going to wind up multiplying this by s plus j omega over s plus j omega minus 1 over 2j. So this is going to be 1 over s plus j omega multiplied by s minus j omega over s minus j omega. So I have 1 over 2j times s plus j omega over s squared plus omega squared minus 1 over 2j s minus j omega over s squared plus omega squared. So now I have s minus s, so the s's cancel out. I have a j omega minus a negative j omega, so that's going to look like 2j omega divided by 2j just gives me an omega in the numerator with a denominator of s squared plus omega squared. All right, that's a good stopping point for today because we have less than a minute of class, and the next couple are a little bit more involved.